Okay, let's take a look at this problem. Don't think it's too difficult, but let's read it. It says a uniform disk, a thin hoop, and a uniform sphere, all with the same mass and same outer radius, are each free to rotate about a fixed axis through the center. So we have the axes, we have different values for these. We know that this guy has mass m and it has a radius r. Same thing for the hoop. It's got a radius r and a mass m. And last but not least, the sphere has a radius r and a mass m. Assume that the hoop is connected by a light, it's connected to the rotational axis by the spoke. That means it actually rotates around that point and just doesn't go sliding off to the right. We put identical forces attached to their rims as shown. Rank the objects according to their angular acceleration from least to greatest. All right, this problem isn't too bad, but it does take 2 steps to get each part. One of the steps that we're going to be using, which is really what we need to do, is we need to figure out what is our net torque on it, so we can use our net torque will give us an angular acceleration. So our net torque over our moment of inertia is going to give rise to our angular acceleration. So let's go through and calculate the net torque for each of these cases. So the net torque for this force is d, which happens to be equal to the radius, d cross into f. So our torque, our net torque, is just equal to, we just have one torque, which is going to be equal to d times f, which is the same as r times f. So this is the torque of our first object. Same thing for this one. We're going to get torque 2 is equal to r times f. Same r down, same f over. I'm dropping off the sign of the angle because the angle is at 90 degrees for all of these cases. So torque 3, again, we get d cross into f, so r, f, and we know that it's a right angle again. So we can see that all these cases that our net torque is going to be the same for each case. So I have rf over the moment of inertia is going to give me my angular acceleration. Rf over our moment of inertia is going to give me my angular acceleration. And for the hoop, Rf over the moment of inertia is going to give me my angular acceleration. So all I have to do is figure out what the moment of inertia of these 3 cases are. That's not that hard because I remember some shapes. I remember that for the disk, the moment of inertia for a disk is equal to 1/2 mr squared. So that's just 1/2 mr squared. With the hoop, I know that the moment of inertia of a hoop is equal to mr squared. This mass is more, it's a larger value. It's more concentrated at a farther distance away. This disk has some stuff in the inside. The hoop has all of its mass around that ring. So I can say that its moment of inertia is mr squared. So my torque over my moment of inertia gives me my angular acceleration. And last but not least, a sphere. The moment of inertia of a sphere, just realized I'm not letting you see this stuff. So the moment of inertia of a sphere is 2/5 mr squared. So we want to rank these in order from least to greatest to get our angular accelerations. So whatever one has the largest angular acceleration is going to win. Well, this is a factor of, instead of writing that 1/2, I can write it as a factor of 2 out front. This has a factor of 1 out front. And this guy, the sphere case, just rewriting that fraction, is going to be 5/2 out front. So 5/2 is the largest case. This is 2.5, this is 2, and this is 1. So my sphere has the largest, my hoop has the least. So hoop is the least, so disk is out and sphere is out. Hoop is the least, sphere is the largest. So hoop, disk, sphere, hoop, disk, sphere. I have actually two of the same answers on my page, but doesn't matter what the answer, it does matter what the answer is, just we determine what the answer is based off of the coefficient in front. This RF over mr squared is common for all three of them. So the coefficient out front will tell us how large our angular acceleration is, or which angular acceleration is the largest. And if we actually look back at this, we can say the sphere is the most compact. It's the one that has all of its mass, or most of its mass, concentrated as close to the axis of rotation as possible. The hoop has the largest, so the hoop is going to be the most resistant to rotate. The sphere is going to be the least resistant, so the sphere gets the biggest angular acceleration.